The fundamental frequency F is the lowest frequency heard when a stretched string is vibrating. The string is now lightly touched 1/3 of the way along its length. What is the lowest frequency heard? And if I was asked to pick the most important, or one of the most important words in this sentence, or this question, I would say lightly. We'll talk about that more in a minute. So over here we have some strings, all the same, and let's draw on the fundamental frequency on the first one. So of course, as I'm sure you know, it's going to be like this. So this is our sort of starting point. We'll let the length of the string be L, and of course we know that C equals F lambda, which means if L is the length of half a wave, that means that lambda for this first one is going to be 2L, which means that we can say C equals F 2L. Right, now back to this word lightly. Now what we'll do is the string is touched lightly about 1/3 of the way along. So let's put a nice green dot there, which is about 1/3 of the way along. Now, if the string was touched lightly, that means that energy can pass through that green point. If the string is not touched lightly, it means that the green point is going to act like a reflector. Now let's imagine what would happen if it acted like a reflector. Firstly, we would have a wave which would travel up and down this bit. Well, it'll be a standing wave, obviously, reflecting back and forth between those 2 points, those 2 nodes. But we'd also have the same on the other side. I've drawn it with a bigger amplitude. It wouldn't necessarily have a bigger amplitude, but we would get this situation. So we would have 2 waves, probably the same amplitude, but one would have a wavelength that's twice the other one. Now this is not what happens. This is what happens if the point is fixed and hard in the middle, but it's lightly touched. So putting our third back, that means that the energy can pass through that point rather than reflect. Again, 2 options that can happen. Firstly, we'll get this wavelength. That will continue and fit onto the string like this. Now that's good. We'll get a standing wave set up that looks like that going through our new green node. What happens if we look at the wave on the other side of the node? Well, let's just take a quick look at that. Move over my string, put the green point back on 1/3 of the way along, which is around about here, and we'll take the wave that forms on the other side, or could form on the other side. Now this one has a problem. Because of its wavelength being 2/3 the length of the string, it's not going to fit into the space that's left. There should be a node here, but as you can see, it's not going to be a node. Therefore, this option cannot exist on the string. It's just not going to happen because we need a node at each end, as I'm sure you recall. So we need to work with this one. So what's the wavelength of this wave as shown in this diagram with the 2 ticks? Well, the wavelength, you can see we fit in one complete cycle into 2/3 of the length. So lambda here is equal to 2/3L. And then we'll put that into our formula as before. C this time equals F prime because, or F1, because that's going to be the frequency, the new frequency that we're hearing, times 2/3L. So we have 2 formulas now. And what we know is that because this is exactly the same string, we're not altering its mass, we're not altering its tension, that the C here and this C there are equal. Therefore, we can now write, moving off to the left, F2L equals F1, which is what we're after, 2/3L. So let's just get a quick formula for F1 out of here. L's cancel. So that becomes F2 times 3 divided by 2 equals our new frequency. Cancel, cancel. In other words, F1 equals 3F. I just need to put my 1 in there. So the answer for this question is D.